Hi, I remember it's been a while not talking about any new contents. It's been 3 weeks. And before the 3 weeks, I think we're just talking about the Chebyshev's inequality and its applications. So the Chebyshev inequality is actually here. It's a formula that we can use to estimate if we are deciding, like, for example, the um, the probability of a value deviating from its mean value or the expected value should be at most like or what at most what percent. So this is the meaning of the Chebyshev's inequality. And the first application is the weak law of large number, which means like uh, the coins, if you toss it many times, that will actually be like half 1/2% of the coins are tossed with head up and half of the with the tails up. And another application is it's another form of the Chebyshev inequality. So it just indicates what's the probability that it is at least what percent of the value are within a certain boundary deviating from the expected value. So that's the second application. And what we left is the third application. It's the Chebyshev's inequality with the Bernstein polynomial. So Bernstein polynomial is actually not very intuitive to think about because it's giving you a very large formula to start with. So how can we first interpret this formula? So at first I would like to introduce it's based on, so looking at its notation, it has a big notation B, capital B, with F, N, and X. So absolutely X is the variable. So what's F? F is defined as a continuous function. So F is from 0, 1 to R. The domain is a closed interval from 0 to 1, and the ranges are the real number. So what is n? N is a parameter. N is a parameter in many distribution we talked about before. For example, like the binomial distribution. N means the number of trials, the number of Bernoulli distributions. So here it's very similar too. So we define it as this one. So if you just remove fkn out, and you'll find out the remaining term, the nk combination x power of k, 1 minus x power of n minus k to sum up from k equals to 0 to n. And that is exactly the binomial distribution. So it's just like a binomial distribution times certain terms, this f out, and f is a continuous function. Okay, and the theorem is that for every continuous function f 1, 0 to r, the supremum of the Bernstein polynomial minus the function itself, well, very close to 0 if n goes to infinitely large. So which means the sequence of Bernstein polynomials converges uniformly to f, to the function itself. So how can we say? So what can we say about this theorem? The main thing is about we can use it to approximate continuous functions with Bernstein polynomials. And that is very useful because imagining in a characteristic polynomials or in the moment generating polynomials, those are unique one to define a distribution. And here the fx can be infinitely many. You can have infinitely many fx, but if we can find out is Bernstein polynomials, we can actually mimic those fx out. So the Bernstein polynomials, well, like uniquely defined fx, not uniquely defined, but you can find a set of fx that is according to that Bernstein polynomial. So that is useful. And this kind of approximation are usually used in computer aided design, fluid dynamics, partial differential equations, and also machine learning, deep learning, something like that. So so its application is kind of wide, although it doesn't look like it. It is like very fun to watch about. So let's prove that why this theorem is good. So the first thing, the idea is to find out, well, because we're finding those two terms are close to zero, we can use some inequalities like Chebyshev's inequality or even Markov inequality, because we're finding it goes to zero. It goes to zero when it's infinitely large, which means it's deviating from its expected value very tiny. So what we first to do here is to give a Bernstein polynomial to form a Sn equal to k, because Sn, the Sn here is defined as here. Sn is the number of success. It's the number of success in n. So if it so if we use the Sn to divide it by n, that's the frequency of the success occurs. So the expected value of f Sn divided by n is equal to that, because we just to move this term out, it doesn't contains about because this is the polynomial, this is the probability, and this is the function. So the expected value of a certain function, which is in this case discrete, can be written in this term. So it's just equal to the expected value of f Sn divided by n. So the Bernstein polynomial can be written can be understood as the expected value of f Sn divided by n. Okay, so second term is to find out the expected value just goes to fx as n goes to infinitely large. So we are no longer consider the Bernstein polynomial, but instead we consider the expected value when we think about the terms of a Bernoulli of like a binomial distribution, which is constructed as like n terms of independent Bernoulli distribution. So so now we can use some facts from the real analysis. So because the 0, 1, this is a closed set of real numbers, so it's compact. So if we know that the f is uniformly continuous, it's because f is continuous on a compact interval, so it's uniformly continuous. That is to say that you can say the boundary is closed, so you can no longer have imagining the tail of f equal to fx equal to 1 over x. When it's close to 0, it goes infinitely large, but in this case it's possible because the 0 is fixed, it at least go to 0, so it's uniformly continuous. So in that case, we can always find I forget what the name of this, delta. Yeah, the delta. So we can always find a delta such that if x minus y is smaller or equal to delta, then the fx minus fy is smaller or equal to any of the epsilon, which is the epsilon can be any number, so it's not fixed here, but the delta is fixed. So in this case, we can separate this. Turns out it's just equal to the expected value of Sn divided by n minus fx. So we can apply the triangle inequality here, because this is a sum of many expected value inside absolute value sign. So if we just like to remove those the one large absolute sign to separate them into smaller absolute sign, then the expected value becomes, well, becomes even larger, because no, that's the triangle inequality. And now we play a very trivial case, very crucial step here. That's to define a identity function. The identity function uh, which assigns all of the elements inside that site into two parts. It's equal to 1 if A is belong to A. If it's 0, so if A is not belongs to A, then it's 0. So in this case, the 1 indicates if only the case happens if Sm minus Sm divided by n minus x is smaller or equal to the delta. And in that case, because we have already find out the if Sn divided by n minus x, if this one is smaller or equal to delta, then its function is always small or equal to epsilon. So in this case, the first term is small or equal to epsilon by our finding above. And for the second case, because we're separating these two terms out, so the first term is Sm is smaller or equal to delta, but the second term is larger than delta. So that is cover all of the possible cases. Those two are that is the magic of identity function. So for the second case, we can find out what's that. It's not smaller or equal to the epsilon, because it's larger. So how we deal with that? This is the probability of larger to delta happens. So we change this term into a probability, and for this term before, the supranom of fx, the supranom of fx is always like larger than any of this fx or fsn divided by n. So it's larger than this term and this term, which means that it takes a minus, and these terms can go negative. So we can treat them as like two double them, but a supranom. Well, if we double the supranom 2, the double supranom will also greater than the absolute value of this formula, of this term here. So instead, we can say it's absolutely smaller or equal to 2 times the supranom fx times the probability given here. So in this case, we are nearly solved the problem, because we find out the term. Let's see, the first term was the first term. Yeah, the first term is the Bernstein polynomial equal to expected value, and we find out the expected value here is smaller than this term. And finally, just use the fact, some like usual practices from the real analysis, and apply the Chebyshev inequality here. So this term is a probability of something larger than a value. So by Chebyshev inequality, this is smaller or equal to this term. So instead, we can find out. We can plug in this term into the polynomial, find out that, and this is like given a certain number, like for example, for the n here, if n is greater or larger than this term, so we combine the delta, the epsilon together. That's how we find out. That's we give a fixed value before, so we can find out all of the term is smaller or equal to 2 times lambda, 2 times epsilon. So that is the case why we say it's go to 0, because anything smaller than any arbitrary positive number is defined as 0 in real analysis. So that is when n goes to infinity is 0. So so for the rest of this course, rest of the of today, I'm going to talk about more about continuous random variables and make a comparison to discrete random variables. So the continuous random variables, they can be different from discrete one because they usually have a, how to say, have a you cannot separate those points out. For example, like if the sample space constructed as all of the points between the longitude and latitude, so you can always find smaller and smaller points between 2 points. So this is a continuous cases. Also, for a selected taxpayer, the income can be anything between negative infinity to infinity. If you treat as like we can have many of the units after the decimal point. And also the precipitation can also be like continuous because millimeters, well, we have 0.0001 millimeters and even more zeros between before the 1. So those are examples of continuous random variables. And one determining feature of continuous random variables is its probability density function. It's called PDF. So so what a PDF means is very similar to the PMF in the discrete cases, or I would say the PDF is just the counterpart of PMF in discrete random variables. So what we define the PDF is that an integrable non-negative function f is called the probability density function. If we can find like the probability between we can find a certain probability between 2 values, then we just need to calculate the integral, the definite integral of the probability density function between a and b. So that's we find out the probability for continuous random variable. So what's the graph? So what's the what we can see that in the graph? It's easier to understand. We see in the graph like this is the density function. This is like density function, which means if it's very high, then it has high probability. If it's very low, then it has a low probability to occur. So the area is just indicates how the how possible a case is. If you say if you see here it's very high and this area will be big. So if A is here, B is here, then this probability will be much higher than this A and B. So if we can find out the integral between A and B, which is the area below, we can find out it's a relative probability according to this density distribution. So that is idea of the probability density function. And there are also some assumptions about this probability density function because it indicates a probability. So the area below the line and above the x-axis is equal to 1 because the value of all of the probabilities sum up to be 1. And also it should be greater than 0 because, well, it should be non-negative because probability can never be negative. However, we can say we don't expect like the highest value is smaller or equal to 1 because it can go very high. Imagining the area determines the 1. So if all of the density function only occur between 1 and 1.1, so the length of the function is the length of the interval is only 0.1, and if the maximum height we set it as 1, so the maximum value possible for the area is 0.1. So that's like that's not what we expect for the area. So the maximum value of the probability density function can go to any value if you like, can go very low, like can go to like 0.01, or it can go to like a million. And also another important property about the PDF is that you can say, because it's continuity, we can always treat a smaller or equal to x with a smaller than x. There's no difference. So these four terms are just the same. So why is that case? So imagining we have a arbitrarily small epsilon. So epsilon, a minus epsilon, a plus epsilon, and the x is in between. Well, so if we set the probability of x equal to a, that is, say, a minus epsilon, a plus epsilon, and x is between. So these two terms is the same defined by the real analysis theorem. So in that case, if we find out this term out, well, that is so close. That is just by 2 epsilon apart. So the definite integral of fx between these 2 points is just the same point. So it's just canceled out when we do the minus. So it's equal to 0. So the probability of a certain value, the x equal to a certain value, is just 0. So which means if we add equal to a equal to b, that is no influence for the entire probability for the interval. That is too trivial to give an influence. But what does FA represent? Because well, we just talked about the height of the PDF, which is the value of FA. So what does that mean? Well, FA can be interpreted as a relative measure of how likely x will take value near A. So if we say the curve is high, then it's possible that x will happen with larger probability. So we can say here, this x as at the center of the bell is with the highest probability to occur, but the probability that x is just equal to that value, that is 0, but it still has the highest probability to occur compared to here. Nearly have no probability to occur. So why that is the case? Because we can find out, well, a minus epsilon plus epsilon, 2 epsilon apart, and we use the 2 epsilon times FA. And that is if the epsilon is not arbitrarily small, it is fixed before, then the probability that the FA curve, the probability that is very, very near to FA, just in this interval, is 2 epsilon times FA. So the epsilon is fixed, is the same. So the probability that x is the probability that x and its close neighbor happening is proportional to FA, the height of the PDF. So let's give one example of the PDF. So the continuous analog to the Laplace distribution. Remember the Laplace distribution. The probability mass function is just like the vertical line with a point here. So, but in the uniform distribution, the PDF defined as 0 otherwhere. But if the x is belong to A and B, the interval AB, then fx is equal to 1 divided by B minus A. And that is easy to understand because the area is 1 and you have B minus A lengths. So the height must be 1 divided by B minus A to give it a constant value, which makes it uniform. The second example is about exponential distribution. So the geometric distribution is usually decreasing with smaller and smaller value in discrete cases. But in the continuous cases, it's called exponential distribution. It's defined as for a parameter lambda, it's defined as lambda times e to the power of negative lambda times x. And x can only be positive, like the geometric distribution. You cannot expect the negative n, or here lambda happens. That is no meaning, because what can we say that uh, all of the cases are failure until -2 times is a success. So that is nonsense based on realistic meanings. And there's another property about the exponential distribution is that if we can find out the probability of x greater or equal to t plus s, given by the condition x is greater or equal to t, it's just equal to probability of x greater or equal to s, because it's covered out. So the probability of x greater, imagine t is like length of that and s is double the length. So this probability given greater than t, which is this part, t and s for the same length, so t plus so this probability given by this probability is just the probability of here because it's covered out. And the next example is normal distribution, also called the Gaussian distribution. The Gaussian distribution formula is very hard to remember, so usually we do not consider its PDF seriously. We usually just use the expected value and its variance to describe the normal distribution. So that is more doable. So the expected value is just its mean, which is the highest point occur, and the variance is the variance is just the standard deviation square. And usually finding out the standard deviation can determine the spread of the bell-shaped curve, its distribution curve. But variance is not really representative in the graph in the graph until we know something like what is the proportion of here 95%. So we can know, well, if we know the in between is 95, then here is 2. Is 2 of the is 2 times the variance, and here is -2 times the variance. But in other cases, we cannot get that information from. So so now I'm sure you are familiar with what's the definition of the probability density function for continuous random variables. So now we're going to move to another topic, which is the cumulative distribution function. The cumulative distribution function is based on the probability density function. It's based on that. But in some textbook, it's also said that we can always find out the CDF first and do the derivative to find out the PDF. But my understanding from the beginning is it's just as this in this sequence. I first learn about the PDF and then learn about the CDF. So if you read some books about CDF before, and usually see some cases like the fx, then it's like it's x d here's no value, it's just 1 d fx. So yeah, usually when you deal with the expected value, and then while your textbook is based mainly on CDF instead of PDF, but here we are generating the CDF from PDF. So the CDF defined is fx, which the capital F, and it's the probability that x smaller or equal to x. all of the random variables values, the realizations that's a smaller or equal to another realization x. So if you can see a graph of that, well, there's no graph, but I think this graph represents that well. So imagine this is a uniform distribution, and the distribution is constructed. The PDF is a straight line, right? And the CDF is like when you meet at A, there's no value, so it's 0. But after B, all of the cases are accumulated out. So all of the cases are already accumulated in the probability calculation. So if you ask like for all of the x greater than b, all of the x smaller than b, then it's 1. Of course, all the x is definitely smaller or equal to b. So after that value is all goes to 1. So that is the idea of CDF. So here is also very similar. PDF is 1/6 for all of value, but the CDF is accumulated. So after 6, you can say all of the value are 6, because if you ask about like what's the probability of x is smaller or equal to 6, it's all of them. Smaller or equal to 100 is all of them. So it's all equal to 1. Well, but how we derive CDF from PDF is given by 2 formulas usually. So the first one, in discrete random variable cases, is we just sum it all up, the PMF, the probability mass function, with the value that is smaller or equal to x. So sum them up, and you can find out just as in this case, 2 smaller 2 is 1, 2, and it's 2/6. 3 is 1, 2, 3, so it's 3 times 1/6, so it's just like 3 divided by 6, or 1/2. Continue the process, continue the pattern, and we can find out CDF. And also in the continuous random variable, in the continuous cases, we just calculate the integral. We perform an integral of like fx from the negative infinite to x. And that is all of the possibility. Remember, in these cases, if we do like this is a PDF, and if we perform an integral over PDF from negative infinite to a certain value, for example, a here, then what we find out is the area of this wide area. And this wide area is exactly the probability of like of the random variable smaller or equal to a. So that's the logic behind. So once we saw these 2 examples before, I will not talk about them for now, but there's some more properties of CDFs I want to talk about. Some of the properties are crucial when dealing with questions in the future. So what properties must a CDF have? First, it is monotone increasing. And secondly, it is right continuous. Third, well, if we take the limit of fx go to negative infinity is 0 and go to infinity is 1. So what does this terms mean? So first, the monotone increasing is like, it is first a monotone function defined as is like it's either always greater or equal to the fx2 is always greater or equal to fx1, given by the x2 is greater or equal to x1, or just inverse, just change the greater or equal to into smaller or equal to, and that is still monotone function. The monotone increasing absolutely is mean it's always you can go flat, you can go increase, but you can never go down. That's monotone increasing. And the right continuous, well, that is continuous from the right. So given by this picture, this function is not continuous absolutely, because they have difference here. have difference at 1, 2, 3, 4, 5, and 6. But it is right continuous because this is the if we give a better sign, this is the 2 is equal to 2 over 6, but all the value here is also equal to 2 over 6. So right, when every point go to right, it continuous. Just think about this point. You can never go to 3. So if we have a very, very close to 3 value here, you can always find an even closer value equal to 3 besides it. So in this case, we say it's right continuous. Right continuous is if you give any point in a function, you can always find its right side is continuous, and that is the meaning of the right continuous. Okay, so and I think the third property is easiest to understand because, well, fx equal to 0 go to negative infinity definitely, because any value that is smaller or equal to negative infinity, the probability is 0. It contains no realization, and if we let x go to infinity, then all of the realizations are smaller or equal to infinity. So we already cover all of the realizations x before negative infinity, before the positive infinity. So the probability is 1. And there are also some proofs about each of the properties. For example, the proof of the first one, why is monotone increasing? It's very easy because we can convert it into the definition. So if we have 2 points, have 2 values s and t, and if s is smaller or equal to t, then which means the set, yeah, this is a set. This is a set that the outcome, the outcome calculated given by the okay, so let's say let's prove it by using the set theorem. If s is smaller or equal to t, then the realization, the random variable calculated version of the outcome is smaller or equal to s, and this set is a subset of a smaller or equal to t because like this, we can say, well, if you're familiar with the term sequence of the set, and this is an increasing sequence of set, and t has a larger value than s, so it's like the s is a subset of t because the union of s and t is just t. That's it. That's like increasing sequence of the set, and by the set theorem, we can always find out like the fs, which means fs is the probability that x is smaller or equal to s, which means the outcome is inside the set s is smaller than the probability that the outcome is inside this set, because this set has more element than this set, and and this is a subset. The S set is a subset of the T set. So in this case, we can write the line of the inequality to find out that Fs is always smaller or equal to Ft, which proves that it is monotonically increasing. For the right continuous, this is a relatively hard proof, and what we mainly use, what the logic we mainly use is to well, to first assume the right hand limit exists, and then try to think about try to find counter examples that it doesn't exist. So that is how we prove is right continuous, and it contains. And I think this proof is relatively hard by current standards. It's even hard. It's even harder than the Bernstein polynomials proving. So I decided to ignore this part. But the main logic is, but I think the most important thing is to remember the property that f is right continuous in the CDF. Then if you like meet with a question like to prove if this curve is a CDF, you can always use these three property to prove it, and that's the most important. And of course, for the last property, for the third property, well, you can say the outcome of the outcome belongs to the negative infinity is zero. So so it's the probability is zero. It's an empty set. And we go to positive infinity, it is the whole set, it's the whole sample space. So probability goes to 1.